Alrighty, in day 2 of week 22, we are continuing to talk about thermal energy. Specifically, we're talking about the idea of conduction of energy, though that's not a word we'll really get using until the end of our lesson. On Wednesday of this week, your midweek check-in, you had the opportunity to interact with these different molecules and see how they moved when they were getting heated up or cooled down, and to see what they acted like at different states of matter. In our class, we talked quite a bit about how these particles act when they're a solid versus a liquid versus a gas. Spent some time observing what happens when we add heat to some of these molecules, or if we cool them back down. And the big ideas that we arrived at with our discussion were the concepts of, well, it seems like in general, a solid tends to have these very compact, tight particles. They're still moving, they're still jiggling or wiggling around, but not as much as, say, in a liquid, where they're moving a little bit more freely. They're not as rigidly locked together. And of course, in a gas, these things are spreading around in every which direction. We actually mostly looked at this for water, and with these particular molecules, since they're a different shape, you can see that they're also spinning. They're not just moving around, but they can also spin. And all of these motions, either in a straight line or in a spinning direction, are showing a greater amount of energy. The solid, which is more compact, it jiggles, it moves, but those particles tend to stay pretty much in the same space. As we add energy again, as we get it to turn into, say, a liquid, what temperature would that happen at? 16°C? Yeah, that's appropriate. So we're at a liquid here, though it's a little bit holding up on top. Should be hanging down at the bottom, filling the shape of the container, of course. But these liquids can interact, they can jiggle around, they can move around. And as we continue to add more water and take them hotter water, warmer and warmer and warmer, eventually starting to boil, and turning this into a gas or water vapor, these things, as you can see, spinning around, traveling faster, moving faster. This really actually connects back to our investigation at the beginning of the week, in which we were looking at different temperatures of water and how they affected the movement of food coloring. When we dropped some food coloring into cold water, it acted very differently than when it dropped into hot water. And while it was a little bit different in each class period, some it seemed like it sunk in the cold water straight to the bottom, others it seemed like it mostly floated up on the top before trickling down. In every situation, it did not spread very fast in the cold water. But in that hot water, it seems like that food coloring spread out very rapidly. Why is that? When we look at something like this quick visualization, it helps us to see why that might be. If I were to trace a particle in the cold water, a particle or a molecule, it would go by very many names, and I'm just referring to each of these little gray circles here as a molecule or a particle. In a glass of hot water, the movement is very different. Just like when we're going from a solid to a liquid to a gas, they move faster, more rapidly. The same is true even within a liquid. And we can trace one of these molecules. I'll just put my mouse in the center here to try to give a visual of where it's going. And while it's definitely moving around, it's obviously staying in a pretty close spot as well. Sometimes it gets bounced around a little bit further, right? But overall, it's staying mostly in the same vicinity. And if I were to leave this for an hour, perhaps it would cover the entire screen. But in this short window of time, it's staying largely in the same spot. Increase the temperature a little bit. How does this affect the movement of a particle? Already we can see that this molecule is covering a greater amount of ground, and it seems like, just looking at the screen, there's a greater amount of blue. There's more space in between the water molecules as they move faster and bump around into one another. They're taking up a greater amount of space also. And of course, I can't even trace it, but when it's hot, they're moving so fast that, of course, oh, that one went off the screen. I don't even know where it went. I'll try to trace one still. all over the place, really. When it gets very hot, these particles are moving around so fast that they're colliding with everything. And one of those things they collide with, of course, is going to be this watercoloring. So as that watercoloring comes in, as this food coloring comes in, as these water particles are going this way and that way and this way and that way and that way and this way, all these different directions, they're going to bump into those food coloring, those drops of dye, and cause them to spread around a lot. This is related to how our ice cube warms up as well. And we'll get into this a little bit more next week, and you'll have the opportunity to model this a little bit. But just have that in the back of your mind. How is it that this movement of gas being very fast moving, pretty hot but spaced out a lot, compared to something like the heat coming from a table, how does this cause the ice cube to melt over time? So what are we going to do? During class today, our big objective is to make sense of this simulation that shows 3 different solids, one that's very hot, one that's kind of medium temperature, and one that's very cold, and to see how energy can transfer between them. To help this make better sense in our brain, let's get a good visual and make sure that color scheme really makes sense. So opening up this one, we can notice that the different particles are moving, but it's even easier if we can track a single one and see that it can move at varying speeds. Sometimes it's slow, sometimes it's fast, depending on what's colliding into it. This is very similar to a bumper car if you've ever been to a carnival, or if you've ever been up to somewhere like Silverwood where they have these activities. Bumper cars are very fun, in which you can go and take your speed and transfer it to somebody else to try to bump them, to push them. And we see that happening with these here. It's going slow, but if it hits something, it might go even slower or even faster, depending. And we can visualize that with the colors. So let's see, let's just watch for a moment and see what color it is. This light pink right now, but it got a little bit faster and it got darker. Now it lost a lot of energy. It's going quite a bit slower. It's that white color scheme. I'm hoping we can get it to turn red to see, and just make sure we know what that looks like too. We might not have the opportunity, but if we look around, we can note some of these red particles tend to be moving quite fast compared to the white ones, which are moving quite slowly. There we go. There's a nice red one, traveling at high speeds. Losing energy, slowing down. So let's take a look at this simulation. Just make sure we have that idea in mind. Again, A, B, or C. Which one of these is the hottest? And how do we know? Of course, we saw those particles that were red were moving very fast, and that fast speed means it's also very hot. If something is moving fast, it is also a warmer object. So A is going to be our hottest, and since C was moving pretty slowly, we know that's going to be very cold. But what about when it looks something like this? What claim could we make about the temperature of it now? I see some individual particles that are very hot, very fast, but also I see some individual particles that are closer to that white, more cold, mixed pretty evenly. What does this mean? We could infer, or we could make a claim that actually the overall temperature is probably pretty evened out. Like if you take a glass of ice water and you set it out on the counter, it's eventually going to come up to room temperature. Those molecules of air and molecules of water and molecules of the glass, they're all eventually going to reach the same temperature. They're going to average out. So let's go ahead and open this one up. You are going to have the opportunity to find this link for week 22, day 2 learning. And this set of slides is just talking you through what you need to do with the simulation. And I'll talk through it briefly here. And I will also give you the opportunity to set loose and go and do this on your own. But as it says, open up this link. This link is to the simulation, and it's a little bit tricky to use. Initially, you're just going to start off with a black screen like this, and you're going to think, what do I do? Follow the instructions. Click that setup button in the top left corner. Okay, let's set it up. There we go. Then click the go button right next to it. Okay, now we're in business. What next? Okay, let's observe it just like this. What's happening within each solid, and why do I think this happens? Again, each of these is a different solid object. We know that one of them is very hot. We know that one of them is very cold. This one being hot, this one being cold, and we could probably infer that this one's maybe somewhere in the middle. Though I guess technically, if we wanted, we could look at this specific information and see just how hot. 300 degrees Celsius, very hot. Minus 235, very, 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 very cold. What are they doing? When we look at A, we see it's got a lot of motion. And if this is lagging as you're watching it on YouTube, maybe, or even if it's lagging as I'm recording it here, you might not see it as well. So view this on your own when you open this up. But we see it moving very fast. These particles are colliding back and forth and up and down and moving. But really, each one is staying in the same place. Same thing over here. They're staying in the same place, but they are kind of bouncing back and forth into each other, trading energy back and forth. What about the white one? Is there movement? Actually, yes, there is. It's very cold, but there is some particle motion. If you look closely, you can see it's kind of flashing this very faint pink on and off. But what if we were to drag it up? That's going to be the next step. What if we were to drag this one up using that slider? What happens over time? What do you observe about this? What's happening in each item? What's happening to A, to the dark red one? What's happening to C, the light colored one? Seems like this one's getting more energy. It looks like it's warming up. And actually, if we look over here at the temperature, we can see that it is in fact getting warmer at the same time that A, oops, moved away from me, that A is getting colder. If we look really close, we can actually even see that these particles that are touching are actually exchanging energy with one another, as if energy overall is getting transferred through this to the opposite side. I guess maybe I can move my hand this way to show it in the same direction. So take some time. Don't just do what I've done in this video. Take some time and actually look at this link. Spend the time to look and see and interact with the information in the simulation. Maybe you can even play around and try some different arrangements. Some students in class came up with some great discoveries. We can reset it down to base. Some students said, "Oh, what if I make this one really cold also?" Right? What if I make this one very cold and I make this one crazy hot? What's going to happen then? Got to reset it, right? What will it do? What do you think if this central item is the only one that's hot and the other ones are very cold? Is energy still going to go to the right, or is it going to go to the left, or is it going to go both directions? Opportunities to play around and do some of your own discoveries. We'll spend a little bit more time interacting with this in class on Monday, but you've had a very brief introduction now to the concept of conduction. Again, like those bumper cars, when one object is moving fast, it can conduct that energy or transfer it to another object. And this allows for heat also to be transferred. When one fast-moving particle transfers its energy to another, it's going to transfer its heat into that other object as well. So what you can do is open up in Google Classroom your exit ticket for today, and hopefully it shouldn't take you more than a couple minutes, but that basic question is, how does the energy get from that left side to the right side? When we have this very hot object on the left, how is it that that energy is transferring across? Talk to me about the motion of the particles. Talk to me about this idea of energy transfer. Overall, how is that causing this to make this fella on the right-hand side warm up? 3-day weekend, Valentine's Day. Next week we're coming back and we are going to have some learning on Tuesday and Wednesday. and asynchronous learning on Thursday and Friday as teachers get prepared to rearrange their classrooms to get set up for students. Hybrid learning starts on February 22nd, and I look forward to continuing our learning journey, both in our current distance model and then a week from now in our hybrid model as well. I'm here if you have questions, reach out. Until then, take care.